Last few days to a week, we've been looking at the Bohr model of the atom. The Bohr model of the atom has three aspects to it that differentiate it from the Rutherford planetary model of the atom. Remember, Rutherford said that the atom consists of mostly empty space with a small, dense, positively charged nucleus in the middle with electrons orbiting around. Those three aspects to the Bohr model of the atom didn't change the basic idea of the planetary model of the atom, but it did kind of qualify a little bit the idea of the electrons and their orbits around the nucleus. That first aspect of the Bohr model of the atom talked about electron levels. The idea that electrons can't just orbit anywhere they want around the nucleus. They've got to orbit on very specific levels around the nucleus, very fixed positions, and each of those levels, each of those positions are characterized by a certain amount of energy. And we talked about electron level diagrams on Friday. You saw those diagrams, and you saw, in fact, that each of those electron levels has a negative value of energy associated with it. The second aspect of the Bohr model of the atom that differentiated it or built upon the planetary model of the atom was the concept that we call stationary states. Electrons, as they orbit the nucleus, experience an acceleration, not because they're speeding up or slowing down, but because they're changing direction. That acceleration, because it's going in a circle, is what we call a centripetal acceleration. It's directed toward the center. Now, Maxwell had suggested back in our last unit, our EMR unit, that accelerating charged particles generate EMR. So according to his theory, these electrons, as they orbit the nucleus, should produce EMR, but they don't. It's not to say that electrons never produce EMR, but as they orbit around the nucleus, they don't. We know they don't because if they did, the energy of that electron would decrease, and as it decreased, that electron would spiral into the nucleus like this. Okay, that doesn't happen. So the electrons don't emit EMR as they orbit around the nucleus. The rules don't apply. It's as if they're not moving. It's as if these electrons, although they're not really, it's as if they're stationary. Finally, the third one, we talked about electron transitions. And there's two types of transitions that electrons can make. One is from a high level to a low level. When electrons fall levels, they give off energy. They give off energy in the form of EMR, or they emit EMR. And generally, that's going to be either infrared, visible light, or ultraviolet light that's given off. Finally, electrons can also jump to a higher level from the first to the third, or from the third to the fifth. As they jump, they absorb energy, and that energy would be in the form of EMR. So they absorb a photon, they give off a photon, depending upon whether they're jumping or falling. Next, we talked about the spectra that can be observed when electrons make transitions. That first one that we showed you was when we had a solid, a liquid, or a gas at high pressure. It's hot. It's at a high temperature, and it's at a high pressure. That emits, of course, all kinds of EMR, not because of the electron transitions. It just emits EMR because it's what we call a black body. It emits all colors of the rainbow. But those colors of the rainbow are all together as white light. When we look at this, we see the light coming off of this solid, liquid, or gas at high pressure and high temperature as being white. But if we introduce a prism or a diffraction grating here, that prism or diffraction grating will split up the light into its component colors, which is all the colors of the rainbow. So in other words, what we see here is a continuous spectrum. Again, nothing to do with electron transitions per se. This is just a reference diagram. The next one we have, typically it's going to be a gas at a high temperature, but at a low pressure. That's going to emit more than one type of EMR as a result of electron transitions going from high to low level. Electrons going from 5 to level 3 to level 2, level 2 to level 1, level 4 to level 1. Electrons make these different transitions, and as they do, they give off a photon of light. Now, when we look at this hot gas under low pressure, it's going to look like white light's coming off it again. It's a combination of a bunch of colors. But it's not a combination of all the colors, because we only get colors corresponding to each transition. But when we put that apparently white light through a prism or diffraction grating, it still splits it up. But this time it splits it up into red, orange, yellow, green, blue, indigo, violet, whatever colors it was that were present in that white light. So the first one splits up all the colors we have, but all the colors are all the colors. The second one splits up all the colors we have, but that's only a few different colors corresponding to a few different transitions. We call the second one a line spectrum, or an emission spectrum, or a line emission spectrum, sometimes a bright line spectrum. Now, the third and final diagram that we have that shows these atomic spectra is what we call an absorption spectrum. Once again, we have the solid, we have the liquid, we have the gas. It's at high temperature. It's under high pressure. It produces white light. We introduce the prism. It splits up that white light. That true white light, which really consists of all the colors of the rainbow, splits it up into the rainbow. It splits it up into the continuous spectrum. But when we introduce this cold gas here, some of that white light that came off of this solid, liquid, or gas at high temperature and high pressure is absorbed by the cool gas. Electrons in the cool gas jump to a higher level by absorbing some of this EMR. And as they do that, no longer do you have this complete continuous spectrum, but rather you have this continuous spectrum over here minus whatever colors were absorbed by the cool gas. That says absorbed, if you can't see that. Minus the absorbed colors. So what you're going to have is this red, orange, green, yellow, what is it, Roy's? Red, orange, yellow, green, blue, indigo, and violet. Same as what we have up here, minus the color right here. So it's the rainbow with a dark spot right there, and a dark spot right there, and a dark spot right there, corresponding to the colors, the photons that were absorbed as the electrons jumped in that cool gas. You can use these spectra, these bottom two spectra, to identify different elements, different gases, different mixtures, by comparing the spectrum that we see of the unknown gas, the unknown mixture, with known spectra. If it matches up, then it must be present. Finally, on Friday, we looked at electron level diagrams, which just show us the different transitions that can take place within an atom, in this case hydrogen, and the energy of each of the levels from which or to which the electrons are going. You can see that my first level, we call it the ground state, closest to the nucleus. It's the one with the highest value of energy, but notice that it's the highest value of a negative energy. The closer we get to the infinity, n is equal to infinity, which is where the electron has left the atom, where it's not really a part of it anymore, we can see that the energies get smaller and smaller and smaller, closer and closer and closer to zero. You can also see that the difference in energy between each level gets closer and closer together, as well as the positions of these lines get closer and closer together. We use these energies in order to determine the energy of a transition. All we have to do with that, it's easy. All we have to do is subtract. You've got to be able to subtract negative numbers, but if you can do that, you shouldn't have any trouble. For instance, if we're making a transition from level 4 to level 2, we're going to say E2 minus E4, final minus initial energy. Negative 3.4 electron volts minus negative 0.85 electron volts. Do the math on that, it works out to be negative 2.55 electron volts. Notice it's a negative value. If we had been going from level 2 to level 4, we would have found that it would have been a positive value, positive 2.55 electron volts. Now that we have the energy of the transition, and therefore the energy of the photon that's either given off or absorbed, we can find the frequency of the photon that's given off or absorbed. And we can do that simply by saying E is equal to H times F. We can find the wavelength by saying E is equal to HC over lambda. One quick little thing here, and then we're going to move on here and answer your question, Patrick. When you're using this equation, E is equal to HF, or HC over lambda, in the context of one of these electron level diagrams, do not ever say E is neg 13.6 or neg 3.4. Don't ever set an electron energy level equal to E. That's not what it means. E is the energy of the photon, and the energy of the photon is always the difference between two levels. So don't ever use that equation in the context of these diagrams without subtracting two numbers. You get that? Okay, that's critical. Okay, I guarantee you this. If you get a question where you're asked to solve for the frequency of EMR that's given off or absorbed between level 2 and level 4, one of the options will be the correct answer. One of them will be using this as your energy. One of them will be using this as your energy. So if you use either one of those as your energy, you'll get an answer that's there, but it'll be wrong because you need to use the difference in energy, the energy of the transition. Patrick, you had a question? No, it's not limited to these 4 series. No, not at all. And these are specific to hydrogen as well, these 4 series. This goes from level, it's going level 1, 2, 3, 4, 5, 6. It keeps going 7, 8, 9, 10, 11, 12, whatever, and there's different series for each of them. The reality is in most diagrams, you don't see past the 6th level because you can see as they get further and further and further up, further away from the nucleus, the lines get closer and closer together. So it's physically difficult to draw it. That's really the only reason. Okay. But no, there are more series as well. I can't remember what they are, to be honest, even in hydrogen. But don't lose any sleep over these names, anyways, right? Because you don't need to memorize those names. You just need to know, you need to be able to recognize the diagram. That's it. All right? I want you to please take a look at multiple choice question number 173 in your worksheet booklet. Let's take a look at 173 now, please. It says we've got selected energy levels of a mercury atom, not hydrogen. Okay, but it's not a big deal because we've got the energy levels. This is more or less an electron level diagram, right? It's not to scale like a real electron level diagram is, but it shows us the energies of each of the levels, which is almost as good. We're asked for the frequency of the EMR that's required to excite mercury from level W to level Z. So we're going from W to Z. First, to find the frequency of that photon that needs to be absorbed, we need to find the energy of the photon and therefore the energy of the transition. So let's say the final minus the initial, Ez minus EW. That's going to be negative 1.6 electron volts minus negative 10.4 electron volts. When I do the math on that, I think it works out to be 8.8 electron volts. Now, understand that we get a positive value here because we're jumping levels. We're going to a higher level and absorbing EMR in order to do that. If we were going the other way around from W to Z, from Z to W, then we would have gotten the same number, but it would have been a negative value. Don't lose any sleep over that. When you go to plug that value into the equation E is equal to HF, just make it positive, whether it turned out to be negative or positive in subtracting the energy levels. Patrick? I'm sorry? Yeah, it'll always work out to be a positive value when you're emitting a photon. It'll always work out to be negative when you're absorbing the photon. But as I say, when you plug it into this equation, we're always just going to make it positive. So we get 8.8 electron volts over Planck's constant, and we're going to use the value of Planck's constant that has electron volts in it. If you don't like electron volts, well, okay, go ahead and convert electron volts to joules there, and then use the 6.63 value of Planck's constant. But anyway, you look at it, you're going to get the same answer, and that is A, 2.1 times 10 to the 15. Now, unfortunately, when I read this question, I like to look at the question sometimes and kind of eliminate a couple possibilities as being unrealistic. There are no unrealistic possibilities here. Okay, there's none that you can eliminate right away here. They're all in that that ultraviolet range of 10 to the 15 hertz, which are all perfectly realistic. Usually, it's going to be infrared, visible light, or ultraviolet. So, 10 to the 14, 10 to the 15, those are all 10 to the 13. Those are all good values that it could be. All right, last thing that's going to be on your test here. Well, the last couple little things that we're going to tie together that are going to be on your test. And then we'll spend a little bit of time going over something else that will be on your exam, but will not be on your test tomorrow, just because it's a little bit much to remember by tomorrow. Okay, this stuff, however, is on your exam. I want to talk about very, very briefly about a guy named Louis de Broglie. It's pronounced de Broglie. It looks like de Broglie. Louis de Broglie took some physics that Albert Einstein suggested, put forth in 1905, and kind of formed a symmetrical analysis to it, a symmetrical argument to it. Einstein said that energy, waves like light really have a particle nature, a photon nature, right? So the particle theory of waves. De Broglie suggested that if waves can have a particle nature, well then why can't particles, like say electrons or baseballs or semi-trucks, have a wave nature? We'll say particles with mass, as opposed to particles like photons, right? Particles with mass have a wave nature. Now, at the time, around 1930 or so, this argument, this theory, was just that, pure theory. There was no evidence to support the wave nature of a baseball whatsoever, or the wave nature of an electron or a semi-truck or whatever. There was no evidence for it whatsoever, other than physics is a pretty symmetrical subject. If this happens, then sometimes, oftentimes, the symmetrical equivalent of it happens as well. If A causes B, then oftentimes B causes A. If waves can behave like particles, then oftentimes, hey, why can't particles behave like waves? So it was purely a symmetrical argument. Now, he did derive an equation that calculated an actual wavelength of particles with mass, but it was still a theoretical argument until some experiments were done with electrons. These electron diffraction experiments verified his theory. These electron diffraction experiments showed that, in fact, these particles with mass do, in fact, have a wave nature. So not only do we have light waves with a particle nature, but now we have particles with a wave nature. So this theory was verified by electron diffraction experiments. What do we mean by that? I'm going to show you a video on that in just a couple minutes here. But I'll just briefly explain it here. Light, when it goes through an opening, diffracts. Light, when it goes through two openings, diffracts and interferes. And it produces this bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, right? It produces an interference pattern. That's what happens with light. That's what happens with a water wave. That's what happens with any wave. We get this interference pattern. If we fire electrons through two holes, we would expect to see not bright spot, dark spot, bright spot, dark spot, bless you, but rather we would expect to see two bright spots behind the two holes, right? You fire electrons through this hole and through this hole, you're going to see two spots where the electrons are detected right behind there. But that doesn't happen. If we fire these two electrons, or we fire any number of electrons through these holes, then what we end up getting is the same pattern as we got for light. The electrons are somehow producing an interference pattern. The interference pattern can only come from waves. So the suggestion here is that electrons aren't behaving like particles as they're going through the hole, one hole or the other. Rather, they're behaving like waves and going through both holes, both openings at the same time, because it's a wave, interfering with itself because it's a wave, and then causing an interference pattern when it hits the screen. You don't need to know a whole lot of detail about that experiment. You basically need to know that de Broglie suggested that particles with mass, like electrons, have a wave nature, and that it was verified by electron diffraction experiments, and kind of roughly know what an electron diffraction experiment is. Now, let's take what we've just learned about de Broglie and his whole idea of wave-particle duality, the idea that particles with mass do have a wave nature, they behave like waves sometimes, and describe our last model of the atom, the currently accepted model of the atom, the one that's been around for about 80 years, longer than any other model of the atom since we've had the Dalton solid sphere model. The Schrodinger model of the atom, named after a guy named Erwin Schrodinger, or sometimes we call it the quantum mechanical model, sometimes we call it the Electron Cloud model of the atom, says, the same as the Rutherford and the Bohr model of the atom, most of the atom is empty space, but there is a small, dense, positively charged nucleus in the middle. It also says that electrons orbit around the nucleus, but in a sense it's a step forward from the Bohr model of the atom, in a sense it's a step backward. It's a step backward in the sense that Schrodinger said, we don't know exactly where that electron is going to be. It can be anywhere within a cloud. Hence the term the Electron Cloud model of the atom. It can be anywhere within that cloud. Now, it's a step forward from the Bohr model of the atom, even though we're less certain about where the electron is. It's a step forward because we're more certain about what we know, or in this case, more certain about what we don't know and what we can't know. Okay, essentially we're saying here that the electrons behave like waves. So they don't have a particular location because it's a wave. Now, we can predict the probability of finding it in a particular location, but that's the best we can do, is make predictions based on probability. Let's say that we wanted to predict right now where Mrs. Sostafachuk is. Where would you guess she is right now? Probably in her office, right? I'd be, say, 75% sure Mrs. Sostafachuk is in her office right now. So we can make a prediction based on probability where Mrs. Sostafachuk is. But that doesn't mean we're right. We're 75% sure she's in her office, just as Schrodinger would have been fairly confident that the electron is where Bohr said it was going to be. We'd find the electron at the Bohr radius, where Bohr thought it was going to be. But that doesn't mean it's there. Doesn't mean it can be found there. We may find Mrs. Sostafachuk within 20 meters of the front office. Maybe she's talking to Nancy at the front office. Maybe she's in the atrium talking to a student. Maybe she's in the staff room. There's probably about a 20% chance that she's not in her office, but she's within 20 meters of her office. The highest probability is where we expect to find her, in her office. Okay, but then she could be a little bit away from her office. There's an even smaller probability that she could be down the science wing at the end of the hallway, or down the math wing at the other end of the hallway. There's an even smaller probability that she could be outside. There's an even smaller probability that she could be over in the church parking lot. There's an even smaller probability that she could be at Tim Hortons. There's an even smaller probability that she could be on a boat somewhere towards England. The bottom line is this. We can predict with some degree of certainty where we'll find the electron. But we can't be sure about that. Okay, it's only based on probability. Where Bohr predicted it would be, okay, this Bohr radius right here, is the most probable location. But there is a certain probability that it's going to be found anywhere within that cloud. It's just the further from the Bohr radius, the smaller that probability is. Does that make some sense? So it's a step back from Bohr in that we don't know exactly where the electron's going to be. Bohr said, we know exactly where it's going to be. Schrodinger says, no, we don't. But it's a step forward in that now at least we recognize that we can't know exactly where it's going to be. So it's a step forward in that we're not pretending that we know where it is. We recognize that we can't know where it is. Right?